Okay, method of sections next. What we do in method of sections is if we only want to find the loads in a few members, it's a shortcut. Here's how it works. You pretend to make your free body diagram in a piece of a beam. You cut the beam in half. So you have internal forces, and by pretending to cut it in half, then you have internal forces on one side of the beam and the other side of the beam. So here's an example that you're cutting this truss in half. You only want to know FBC, FGC, FGF. You don't want to know everything. You have this load right here. And we have the second half, by the way, over here. So, like the method of joints, we find the overall loads, 1,000 newtons. Well, what's it going to do at D and E? E is a roller, so it's just one directional. And you know, I might be wasting some time. I just got to thinking. If I'm analyzing this, only this is the free body diagram on this, I don't have to worry about this. I don't know what my reactions are. Okay, let's move on. So that's the idea of the method of sections. Let's go ahead and compute this. So we have 1,000 newtons down, FGC up at 45 degrees. So we can write down FGC that would be what? Sine 45 degrees? Minus 1,000 newtons equals 0. So FGC equals 1410 newtons. I believe that's correct. So in the y direction then, FBC minus FGF cosine minus or plus 1410 cosine 45 degrees, which is 1,000 newtons, equals 0. Plus, plus, minus. Okay. So we have two unknowns. Now we need a moment equation. Let's take the moment about G. Moment of G. The reason for doing that is we eliminate two variables. So 1,000 times 2 to the positive, 1,000 Newton, or excuse me, 1,000 times 2 is 2,000 Newton meters. And FBC acts in the clockwise direction, so it would be negative. Minus 2 FBC would equal 0. FBC then is 1,000. Which would mean FGF has to be 2,000. newtons, excuse me. Ooh, this is a lousy unit. Newtons. And the units here would be Newton meters. Okay, so that's how we use the method of joints. We look at the free body diagram of this, and initially I said, oh, find the reaction forces, and then I caught myself and I said, no, wait a minute. I don't need the reaction forces to find this information. Okay, another example. So similar, we have a couple forces on this portion of the beam of the bridge, so we can cut it, and we will need, now last time, remember, I said we didn't need the reaction forces. That was because our free body diagram of the piece, of the section, did not include a reaction force. In this case, it does. Whether we take the left half or the right half, we need to find the reaction forces. So let's do that. So we have 1200 newtons has to equal, well, we're going to have AY. I'll take AX to be a positive value, and dy. Because this is a roller here, we don't have any y coordinates. So AX has to equal negative 400 newtons. So AX plus 400 newtons has to equal 0. Okay. AY plus dy minus 1200 has to equal 0. Now we have two unknowns, so we need one more equation, probably a moment equation. The easiest one is to take it around A. Moment around A has to equal 0 equals 12 dy counterclockwise, so it's positive. And then the other two are clockwise, so that's 8 times 12, 9600. 8 meters times 1200 newtons. And then 400 times 3. And the units would be Newton meters. So we can calculate dy. That would be 900 newtons. And from that, I made a mistake here. I got to change that to a negative. There we go. So dy is 900, ay has to be 300. Okay, dy, ay, and we don't really need ay, but will need dy for sure if we consider the right-hand side of the bridge. So circle this up. I suggest you guys do examples Make sure you can follow the examples in the video. Try the other examples in the book. And let's see what happens. AY is 300. AX is 400. DY is 900. Is that what we got? DY 900, AY 300, and AX 400. And they have it going in the other direction, by the way, which is our sign change. My sign is different because of I drew my arrow in just the reverse. So my number is going to be negative. And with that, I'm going to end this video here and go the rest of the way. The book's going to do the diagram of the left portion of the truss, since it involves the least number of forces. Which, hey, simplify the problem if you can. Next video.